Have you ever opened a bottle of perfume or soda and instantly noticed the smell of it? This happens because liquids tend to evaporate, and the evaporated molecules exert pressure called vapor pressure. In a closed container, equilibrium is reached between evaporation and condensation, and the pressure at this point is what we study in chemistry. In this video, we'll understand vapor pressure in liquid solutions, how Raoult's law explains it, and how it behaves in different types of mixtures, whether we mix liquids with liquids or solids with liquids. Let's define what is vapor pressure. Vapor pressure is the pressure exerted by vapors in equilibrium with their liquid or solution at a given temperature. The higher the escaping tendency of molecules from the liquid surface, the higher the vapor pressure. In a closed container, evaporation continues until the rate of condensation equals the rate of evaporation. At this dynamic equilibrium, vapor pressure becomes constant. When two volatile liquids are mixed, both contribute to the vapor pressure. According to Raoult's law, the partial vapor pressure of each component is directly proportional to its mole fraction in the solution. P is equal to X times P. P1 equals X1 multiplied by P1 naught. P is equal to X times P. P2 equals X2 multiplied by P2 naught, where P and P are partial vapor pressures of components 1 and 2. X and X are their mole fractions in liquid phase. P and P are the vapor pressures of the pure components. This means if you know the mole fractions and the pure component vapor pressures, you can calculate how much each component contributes to the overall vapor pressure of the solution. To find the total vapor pressure of the solution, we add the partial pressures of both components. This gives us P total equals P1 plus P2. Now substitute the values from Raoult's law. P total equals X1 times P1 naught plus X2 times P2 naught. So what does this mean? X1 and X2 are the mole fractions of the two components in the liquid phase. P1 naught and P2 naught are the pure component vapor pressures, and P total is the overall vapor pressure exerted by the solution at equilibrium. In other words, each component contributes to the total pressure in proportion to how much of it is present in the solution. The total vapor pressure is P total is equal to P plus P is equal to X times P plus X times P. We can also write it as P total is equal to P plus PP times X naught. As mole fraction X increases, the total pressure shifts toward the more volatile component. To find the composition of vapor phase, we use Dalton's law. P1 equals Y 1 times P total. P2 equals Y 2 times P total, where Y1 and Y2 are the mole fractions of components 1 and 2 in the vapor phase. So, Y equals pi divided by P total. This shows that vapor phase is richer in the more volatile component, even if the liquid phase is equimolar. Let's compare Raoult's law and Henry's law. Henry's law states P equals Kh times X, where P is partial pressure of a gas, X is mole fraction of gas in solution. Kh is Henry's law constant. On the other hand, Raoult's law is expressed as P equals P0 times X. So, if we treat a volatile liquid as a gas over a liquid solution, we see that Kh equals P0. This means Raoult's law is a special case of Henry's law, applicable when the gas is actually a volatile liquid component. Now let's consider when a non-volatile solute is dissolved in a volatile solvent like salt in water. Here, only the solvent contributes to vapor pressure. Let X1 be the mole fraction of solvent P10 P. 1 naught be the pure solvent vapor pressure. Then P1 equals X1 multiplied by P1 naught. This means adding a non-volatile solute reduces the vapor pressure. Why? Because solute particles occupy space at the surface, reducing the number of solvent molecules able to evaporate. There are two key reasons why vapor pressure drops when a non-volatile solute is added. Surface area for evaporation is reduced. In a pure solvent, surface is fully available. In a solution, solute blocks some surface. Fewer solvent molecules escape. Less evaporation means lower vapor pressure. This is known as Raoult's law for solutions of solids in liquids, and it explains key colligative properties like boiling point elevation and freezing point depression. When we plot vapor pressure against mole fraction, here's what we observe. For an ideal solution, the graph is linear. Each component's partial pressure increases linearly with mole fraction. Total vapor pressure lies between the two pure component pressures. This helps us visually understand the behavior of ideal and real solutions. Let's review what we have learned. Vapor pressure is the pressure of vapor at equilibrium with its liquid or solution. For liquid-liquid solutions, Raoult's law gives us partial and total pressures based on mole fractions. Raoult's law becomes a special case of Henry's law for volatile liquids. In solid-liquid solutions, adding non-volatile solute reduces vapor pressure.